Today we're going to talk about trig functions of any angle on the coordinate plane, and this is different than what we were doing the last 2 days in class, because previously we could only do trig functions if we had an angle or a reference angle of 30, 45, or 60 degrees. So we're taking that limitation off, and we have some abilities to calculate trig ratios of angles that don't fit those three measures. So before we get started, we have to talk about the general definition of trig functions. And I'll give you some time to jot this down. We're going to let theta be an angle in standard position with the point xy on the terminal side of theta. We'll talk about that R here in just a little bit. But you can also draw that picture. We've got a coordinate plane and then there's a circle there. So we're going to talk about how the circle relates back to this R that we're going to talk about. Now, I'm going to pick some arbitrary point anywhere on the coordinate plane. It could be in quadrant 1, 2, or 3. Any of them, 1, 2, 3, or 4. Any of them would be acceptable. And for the sake of my drawing, I'm just going to choose a point somewhere in quadrant 1, and I'm going to label it. One moment. I'm going to label it XY. Now, I could have picked a point anywhere and labeled it XY. Would have been totally fine. I want to pick that point XY. So I'm going to ask you the question. If I just give you an ordered pair XY, how do you move from the origin 0, 0 to get to XY? Give me like the words directions. If I was standing right here at 0, 0, where would I have to go?
The right on the X.
I'd go right X units, and then I would go up Y units. Do you agree? Okay. And that would be true in any of the quadrants, right? I would go left X units and down Y units in the third quadrant. Or I could go right X units and down Y units in the fourth quadrant. So no matter what quadrant I'm in, I would still call those sides X and Y. Now, the reason I have this circle here is we're going to draw in an extra side, and it's going to connect your XY to your origin, 0, 0. And we're going to call that specifically R for radius. That's why I have the circle drawn there. You'll see a little bit later, I'll kind of just like ignore the circle. But that's why we have R in our definition, is we're going to call the hypotenuse of this right triangle R for radius, so that if I took this point XY and moved it around the circle, I would always have the same radius, no matter what quadrant I'm in. So we have this nice right triangle. Right angle right there where I turn, go to Y. And we're going to talk about angle theta as defined in the general definition. So if you reread your general definition, it says, let theta be an angle in standard position. So it has to have an initial side on the positive x-axis, whose terminal side contains the point xy. So my r is part of my terminal side. So I could label theta right there. And when we're working on these problems, theta in our triangle will always be right around the origin, because then that fits the definition of the standard position angle. So it'll always be right around the origin. Can you find the 6 trig ratios of that triangle? Sine, cosine, tangent, and then cosecant, secant, cotangent, as I have it labeled. Would you be okay with that? Yeah, what sine? Y over R. What's cosine? X over R. And what's tangent? Y over X. To write out your reciprocal functions, you would just do what with those? Flip them, make the reciprocal. So it would be R over Y, R over X, and X over Y. Now the only thing that still remains an issue is if I'm giving you just the point xy, you really need to know what the radius is, because if all you have is x and y, you can't do all the trig ratios. So we need to find r. How might you find r if you knew what x and y were? Okay. Sure, it's a right triangle. You could use the Pythagorean theorem, and you'd be solving for the hypotenuse. So if we wanted to solve for r, we could set up something that looks like x squared plus y squared equals r squared. And of course, we would know x and y, so they would be numbers. We would plug them in, square them, add them together, and have a number equal to r squared. And how would you get r all by itself? Square root both sides. Absolutely. Thanks, Kyle. Square root both sides. So r in this definition is the square root of x squared plus y squared. And you can fill that in. Now, you can either memorize r equals the square root of x squared plus y squared, or if you'd rather, you could always set up that Pythagorean theorem. So you could do x squared plus y squared equals r squared, and then square root both sides. Okay, so it's kind of up to you. They're doing the same thing. If you memorize r is the square root of x squared plus y squared, you just don't have to do any steps for solving. Okay. Now, even if I put my xy somewhere else in the coordinate plane, those things would all still be true. My opposite side will always be y, my adjacent side will always be x, and my hypotenuse will always be r. So those statements, y over r, x over r, y over x, those are true for sine, cosine, tangent in any of the quadrants. Okay. So let's put this to use in an example. And my first example, I use a visual to kind of present it. So I've got sort of that same picture going on. I've got the coordinate plane, the x and the y-axis. I have a point labeled in the fourth quadrant, 3, negative 3. And I want to find the 6 trig ratios of the angle theta. The angle theta, remember, being in standard position, formed by the initial side on the positive x-axis and the terminal side passing through the point. There are 2 ways to approach this problem. One is purely algebraic, and that requires you to really know the last slide that we talked about. So if I'm going the purely algebraic route, I can look at the point 3, negative 3, and I could label those as x and y. The only other thing I would need in order to be able to find my 6 trig ratios would be the value of r. And I would use what I wrote in my definition. R is equal to the square root of 3 squared plus negative 3 squared. Notice how I use parentheses around my negative 3. That's important if you're using a calculator. What happens when you square 3 and negative 3? They both equal what value? 9. And they'll both be positive 9, right? When you square in that radius piece, you'll never have a negative number there. Okay? It will always square to be positive. So then you really have 9 plus 9, which is the square root of 18. And what should you do with the square root of 18? Simplify it. Most of us use the factor tree to do that. Okay, so off to the side, you could work with the square root of 18. Factors of 18 are 9 and 2, 3 and 3, and you're looking for factors that come in pairs. So we could really call that 3 square root 2. So remember, I have x is 3, y is negative 3, and now I know r is 3 square root 2. If I know my general trig functions, my general definition, then I can just plug in. So I would go back to like what we put on the last slide. The sine of theta is y over r. That's negative 3 over 3 square root 2. The cosine of theta is x over r. That's 3 over 3 square root 2. Tangent of theta is y over x. That's negative 3 over 3. I'm not doing any simplifying just yet, but I'm just showing you, like, purely algebraically, if I know those things are true, y over r, x over r, y over x, I just plug them in. Now, I should simplify some of those ratios correctly. So, sine and cosine, I have a radical in the denominator that I'll have to move, so I've got to rationalize my denominator for both of them. I'm going to multiply by the square root of 2 on the top and the bottom. Remember that in the denominator here, when you take a square root of 2 times the square root of 2, it doesn't just disappear, it just makes the square root disappear. So it's really now 3 times 2 in the denominator for both of those. So up in the numerator, I have something like negative 3 square root 2 over 6. And here I'd have positive 3 square root 2 over 6. Are we okay with how I did that? Okay. And then I should go through and like simplify, reduce, just like always with fractions, you want them to be in their simplest form. So like in the numerator, 3 and 6 will cancel, or not cancel, but they'll reduce to be 1/2. So 3 goes into 3 1 time, 3 goes into 6 2 times. Same here, 3 goes into 3 1 time, 3 goes into 6 2 times. So I come up with something like negative square root 2 over 2, positive square root 2 over 2, and then down here it would be negative 1. Does anybody have any questions about how I got those? Now here I'm going to talk about like a little hint to help you do the least amount of work, because you know I always like to work smarter, not harder. After you would do these basic trig ratios and you come up, you rationalized, you simplified, you did everything, you should go back and you should, if it's asking for 6 trig ratios, you should do cosecant, secant, and cotangent. My hint to you is, if at any point in sine, cosine, and tangent you rationalized, don't flip your final answer, because then you'll have to re-rationalize, which rationalizing is sometimes not hard work, but it's more work than we want to do. So in the case of sine and cosine where I did have to rationalize, when I go to do cosecant and secant, go back to the very first thing you wrote down for y over r. When I initially did y over r, I did negative 3 over 3 square root 2. So I would think about cosecant as r over y, and I would flip that and make that 3 square root 2 over negative 3. But if you flip the original fraction, then you'll move the radical up to the top and you won't have to rationalize again. You'll only have to simplify it. Negative 3 over 3 will be negative 1, so you'll just have negative square root 2. And then the same thing for the secant. I would go back and I would really just do r over x. And then flip it. So that it was 3 square root 2 over 3, which is just a positive square root 2. A lot of people are used to going to the back and just like flipping sine, flipping cosine, and flipping tangent. But if you flip your answer, you'd create another thing you'd have to rationalize. You'll come up with the same answer, you just got to do more work. And then the reciprocal to cotangent will be negative 3 over 3, which is still negative 1. So that one had a lot of work in rationalizing and simplifying. But what I presented to you was like a purely algebraic way to do it. If you know the definition for the trig functions on the coordinate plane, y over r, x over r, y over x, you're good to go. Before I leave this slide, let me just say, if you have trouble remembering those general definitions, you could approach this more like a geometric problem in drawing the actual triangle. So I never actually drew the triangle, right? I just said, let me pick my point x and y, and let me find my r and move on. You could draw the triangle like we did when we first did the definition. So I'm going to go to this picture. And if my x is 3 and my y is negative 3, I could draw from the origin. I'd have to go right 3. I'd have to go down 3. And then I'd have to find my r. But I would have a right triangle where I could do SOHCAHTOA. Opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. I'd come up with the same answers. Note that this is a little bit different than geometry. In geometry, you would never label that side negative. Excuse me. I must get a formaldehyde. Taking it in, talking. I'm joking. I'm fine. But in algebra, it's okay to say that your side is negative 3. Okay. Let me give you a problem to try at your desks. Okay? And you can approach it if you want to draw the actual triangle shape, or if you would rather approach it with just x, y, and r, you can give that a go if you're thinking you might like that a little bit better. So I want you to find the 6 trig ratios if the point 8, negative 6 is on your terminal side.
As I'm walking around, you guys are doing a really great job, and I'm seeing sort of the two different approaches. Some people started with a drawing, and that's great. If you prefer to see the actual triangle, that works out awesome. Just remember that the X and the Y will form the legs of your right triangle, and then you'll be tasked with finding the value of R. And some of you might then just use Pythagorean theorem. You might just say a squared plus negative 6 squared equals R squared, and then you go through and you solve. Okay. Others have left that drawing out, and that's not a big issue either. Okay, you can do it without the drawing. And they just started with what I have at the very bottom of the screen right there, R equals the square root of 8 squared plus negative 6 squared. Either way, R comes out to be what value? 10. And so I was being nice to you here. And if you're using the algebraic method, you can call X is 8 and Y is negative 6, and you're ready to go. If you're not as comfortable with the algebraic definitions yet, you can still go to this triangle. Remember that theta is always at the origin. Negative 6 is your opposite. 8 is your adjacent. And 10 is your hypotenuse. So you could still run like a SOHCAHTOA. Either way you do it, the sine of theta by the algebraic definition is y over r. That's negative 6 over 10. By the geometric definition, that's opposite over hypotenuse, which is negative 6 over 10. So either way works. Cosine is 8 over 10. And tangent is negative 6 over 8. And you should do what with these fractions? Simplify, reduce. So we would have negative 3/5, positive 4/5, and negative 3/4. And then after I simplify them, I can flip them to get my reciprocals. Bless you. Negative 5/3, 5/4, and negative 4/3. And I have my 6 trig ratios. Let me ask you this question. Which quadrant is that point located in? 8, negative 6, quadrant 4. And think about all students take calculus. What's supposed to be positive in quadrant 4? Cosine and secant. Look at your ratios that you have from the general definition. Is that true? Yeah, the cosine is 4/5 and the secant is 5/4, and then everything else is negative. So what we had decided on for all students take calculus the other day in class, that still works here. Okay. In the fourth quadrant, only cosine and secant will be positive. The last thing we want to discuss are something called quadrantal angles. We have not yet taken or found the trig ratios for these quadrantal angles yet. We're going to do that today. Once you get used to them, they're actually pretty easy. There's only certain numbers you can use here. What word is in quadrantal? Quadrant that we've been using. Yeah, quad's in there, but quadrant, we've been using that a lot, right? So quadrantal angles are the angles that make up the quadrants. If you think about that, that means that your terminal side has to be on either the y-axis or the x-axis so that you form one of the quadrants. And they have to be multiples of 90 or pi over 2. So like when you're doing your coordinate plane, you're building your coordinate plane, you start at 0, 90, 180, 270, 360, 450, 540, 630, 720. Those are all multiples of 90. And then as you go around for radians, you're always adding pi over 2. 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi. Okay, so you're just going up by pi over 2 each time. Okay.
when we evaluate trig functions of quadrantial angles, we'll use something called the unit circle. And this is the only time we'll really talk about the unit circle. Although, if you take Algebra 3 next year, which a lot of you might be doing, you'll learn all of the unit circle. So you'll do a lot more. So we're going to draw a picture very similar to the one we saw on our first slide. A coordinate plane and a circle. And this circle now is going to specifically be the unit circle. On the other problems, those were just circles with different radius lengths. Okay, this one will always have the same radius. I'm going to label 4 points that you'll need to know. This is 1, 0. This is 0, 1. This is negative 1, 0. And this is 0, negative 1. And this is on your little half sheet, too, if you remember. It's up in the corner. If I label those 4 points and I ask you, what's the radius of that circle? Faith says it's just 1. You're going from 0, 0 to any one of these points. How far do you have to move? 1 unit. So the radius is 1. The radius is 1. The radius is 1. The radius is 1. All the way around, right? Okay. And think about how this could be helpful using the general definition that we had at the beginning. Here you have x and y with a radius of 1. Can you find sine, cosine, and tangent then? Yeah, no problem, right? Y over r, x over r, y over x. So that's what we're going to use this unit circle for. Unit circle means the radius equals 1. The last example you did, the radius was 10, so that was not a unit circle. It's just a circle. Yeah, because if we had a point here, Faith asked, even if it's not a triangle, can we still do that? Yeah, because that's the general definition of the trig function. But if you had a point here, you would just draw back to the x-axis, and you can't make a triangle, right? But the y over r, x over r, y over x, those things are true anywhere around the circle, even on the axes. Good question. Okay, so let's look at an example here. Evaluate the 6 trig ratios for theta equals pi. Some people might know where pi is on the coordinate plane. Other people might choose to convert that into degrees. Either is acceptable to me here so that you can decide where you're located. If you convert it into degrees, you should take pi times 180 over pi. And then that's really just equal to 180, right? Where is 180 on the coordinate plane? Over on the left side of the x-axis. What's that point on the unit circle? Negative 1, 0, right? You have to go left 1, up or down nothing. So this is the point, negative 1, 0. And you'll have that when you're taking the quiz and the test. It's on that sheet that I gave you. But there's my x and my y. What's my radius? 1. I'm ready to go. The sine of theta is y over r. That's 0 over 1. Okay, 0 over 1. So 0. the cosine of theta is x over r. So that's negative 1 over 1. Or negative 1. The tangent of theta is y over x. So 0 over negative 1 equals 0. When you do quadrantal angles, you're going to get lots of zeros, lots of ones. And if you did the cosecant of theta, that would be r over y, right? Which would be 1 over 0. What do you know about 1 divided by 0? Can you divide by 0? No, what do you call that answer when you can't divide by 0? Jace? Undefined. Yep. Someone else said it too. So when you do quadrantal angles, you're going to have a mixture of 1s or negative 1s, and then 0s and undefineds. Because the reciprocal of 0 is undefined. The reciprocal of undefined is 0. So secant of theta is negative 1, and cotangent of theta is also undefined. Anytime you have a 0 for 1, the reciprocal is undefined. Vice versa. You have undefined in the beginning, then its reciprocal is 0. Here's your homework assignment.